Hello, I'm Dulce Ordaz, and I'm going to present my argumentative exam. First, the situation number one asks us to derive the expression of Biot-Savart law. So first I put a wire here, and where the current is in direction of the positive z-axis, and the line differential must go along the direction of the current of the wire. So it goes also in the positive z-axis direction. Then we must put an observation point, and the distance from the observation point to the wire is rho. So following this line of reasoning, the vector of r is drawn from the source to the test point, as we can see here. Then we r is the separation vector, so we make a subtraction from rho unit vector rho and z unit vector z. And mathematically, the L, as it goes in this case in the direction of z, we use the line differential as this z unit vector az. And for the magnitude of r, we simply put r rho square plus z square. And to obtain the direction of this cross product, we only make the cross product of the line differential and the unit and the vector of r. And we also have to remember that we are using the cylindrical coordinates as we can see here. And finally, we just need to change the previous values in the Biot-Savart law formula as we can see here. And then using this triangle, we can obtain the angle that it's alpha. And from this expression, we can derive the rest of the Biot-Savart law formula. And in this case, we're gonna solve this integral with trigonometric substitution, and in this case with tangent. Finally, we obtain cosine of alpha 2 and cosine of alpha 1. In this case, cosine of alpha 2 is the one that it's up of, in this case in B, and the alpha 1 is the one that is in the other side. And for solving for these angles, we must do the law of cosines. And we make here all the explanation. And finally, at the Biot-Savart law formula, we simply replace cosine of alpha 1 and cosine of alpha 2, and we obtain this. In this case, the Biot-Savart law intensity is h, so we only have to multiply for the permeability of free space to obtain the magnetic field, which is B. Then a square current loop, it's here, and we must obtain the magnetic field intensity in order loop. And we use the superposition principle that it's only the sum of each segment of the loop. And I use the distance between 2 points to obtain the distance of A, Z0, and C, that it's this one, using maybe the Pythagorean principle. And for the direction, we use the cross product, as we can see here. And in the main formula, I simply replace these values from here. So I just replace and add my unit vector. I make the same for segment number 2, which goes in the negative direction of y. And then I make the cross product. In this case, I obtain two directions, that it's in the negative direction of z and negative direction of y of x. And I verify this with MATLAB, but I'm going to explain this later. And I make the same for the segment 3. In this case, I have some confusions about the rho, but in this case, rho is like extends. That's why it have a different value of than simply rho, because it is upward. And also I obtained two directions in this case, and for the segment number 4, I obtained the unit vector x. And I simply, for the superposition principle, I add all the magnetic field intensity that I obtained for each segment, as we can see here. And I verify with MATLAB the direction. Here it's in the, I use some values, educated values, and I verify that in this case, it's in the positive x, as we can see here, y, sorry, as we can see here, and the segment 2, negative y, x, and negative z, as we can see here. And the same for segment 3, negative y and negative z here. And only positive x at the segment 4. And then going for the situation number 2, the magnetic field due to a circular loop in the x set plane. First, I have the observation point at the y-axis, that it's y0. I have my integral, and I use the separation vector to obtain the distance from r from my loop from the point to my loop. And I make these equations, and then using my diagram of symmetry, I can see that the horizontal components are canceled out, so only the magnetic field of this observation point goes in the direction of the y-axis. And using my right hand rule, curling my fingers in the direction of the current, that is something like, like this. Well, the direction of the current, that it's clockwise. My thumb points in the direction of the magnetic field, and this because we are viewing the loop at the positive y. Then I make my cross product for a negative rho, which is here, and y0. And note putting y0 and the unit vector set because this is the height and not the coordinate. This also tells us that the derivative, well, I obtained this a set that tell us that the direction of h. Also, I have to remember that a set talks about the height of the observation point and not exactly about the set coordinates because we are at cylindrical coordinates. Then I simply replace all my values in the integral, the r, and the magnitude of r that it's here, and the unit vector and the cross product that it's here. And phi is my integration variable, so I solve for phi, which is 2 pi because we're talking about a circle, and pi, and 0 because it's the full circle. And we can be here that, and here we see that in this case the integral cancels out because a set and a rho are perpendicular. So I solve for this part of the integral and I obtain this. Then going for the negative, well, seeing my observation point from a negative y-axis, I did exactly the same, but I changed some values. As we can see here, this one is positive because it's in the positive direction, and this one is negative. And also here they are perpendicular, so they cancel out. The same happened at the horizontal components, but in this case, as it goes in the negative y-axis, the vertical component doesn't cancel out and it goes in the direction of the negative y-axis. Then the magnetic field due to an infinite current sheet, Ampere's law. And then, first I have to use Ampere's law and add an infinite current sheet on the y-z plane, as I draw here. The current density is flowing in the negative z direction, as we can see here, at an observation point at the x-axis. Then I draw this for display my parallel x-axis, well, my parallel segments as the problem asks. And using my right hand rule, my fingers go in the direction of the current and my thumb, which represents the direction of the magnetic field that it's pointing towards the y-axis. Well, what I did here is simply display like my problem, and then applying the symmetry of field direction, I have that the magnetic field is uniform in the y direction, explained with the right hand rule, which I explain here. And this is because we're dealing with that uniform surface current density in the negative z direction. So using the right hand rule with respect to the current direction in negative z direction, the magnetic field above the sheet is pointing at the positive y direction, and the magnetic field below the sheet is pointing in the y direction. This using the parallel segments that the problem is asking us. And to evaluate the integral, I use Ampere's trajectory, but I split the integral in 4 segments, like the segment of the sheet. In this case, I use like the segments are not infinite in this case, but only for reason of simplicity. And segments 4 to 1 and 2 to 3 do not contribute to the integral because the sides are in the y-axis, which the magnetic field, where the magnetic field is parallel. Also, because these sides are taken as the infinite sides of the sheet. And then I solve my integral of the ampere's trajectory, but I like divide my integral using just the magnetic field intensity, and then I just simply multiply by the permeability free space constant. Here, as we can see, it goes in the direction of the negative y, as we can see here. And I just multiply and they turns into negative. And the segment 3, 4, I did the same, but in this case, they go in the positive y-axis, positive direction. And I make my integrals. Well, y, it's my variable to the dy. And I integrate from L halves, L is the length, to minus L halves. Then the other segment is from negative L halves to positive L halves. And they got the same value. I just add them, and as I needed to use the current density K and mu to 10B, I simplify using the formula that we already know of current density, and I replace in the integral. And then discussing the physical interpretation. The direction at x0 is this one. It's in the direction of the unit vector y. And for minus x0, it's the same, but in the opposite direction. This was determined by the right-hand rule. Therefore, it can be seen that the magnetic field goes from x0 to minus x0, which represents a discontinuity in the magnetic field along the sheet. To obtain the constant magnetic field, it is necessary to do the difference of both B, as we can see here. And this result is expected as a field B is constant along the sheet. Then comparing with a solenoid, where B changes respectively to the distance, an infinite sheet, we have a constant B in both sides. Then going to the situation 4, where we have a particle with a charge, a mass, and located at the origin T. And these are the initial conditions. And applying Lorentz force law, here, the velocity vector, I put the negative velocity y, because as we can see here, and using the second law of Newton, I simply replace the value of force here at the Lorentz force law. And then I replace these components that we already know at this formula. And I obtain this. Then I make the cross product for velocity vector and magnetic field vector, and I obtain these values. And I again replacing the equation, and then I match the components with the corresponding components. For example, I match the velocity, x velocity, with the magnetic field and BZ, because they go in the direction of the unit vector x. I did the same for y and for z. And By is my constant because the derivative of a constant is 0. And I replace the values, as we can see here. And this is an ordinary differential equation linear system with constant coefficients and homogeneous. Now using tables, I replace the values to obtain the PZ that it's here. And then I did the same for the velocity vector. And I have here. And I to determine A, B, and C, I use the initial conditions that are time equal to 0 and velocity, it only goes in the negative direction of y. And I replace my values. I obtain that A is equal to 0, and C is also equal to 0, and B as well. And when A and B are equal to 0 means that there is no motion at x and z, because they were at the unit vectors of x and z at the beginning. So I obtained these values. And then I decided to use the cross product for the initial conditions to see if my result is accurate. In this case, to see that the 3 zeros that I obtained are accurate. And I did the cross product. Only y it's going, well, only the velocity it's going at the unit vector y, and magnetic field as well, but at the negative. Then I replace these values at Lorentz force and I obtain zero again. And we can see with this that at all time t, the velocity is parallel to p, and this can be seen here. And following this line of thinking, there is no Lorentz force in consequence as there is no acceleration along the path of a particle. Then we can say that the particle moves in a straight line motion negative to the y-axis with a constant velocity to the no acceleration. And then determining the position vector, I obtain that the particle doesn't move along x and z axis and only moves along the y-axis with respect to time. As we can see here, the velocity is the same, but just the derivative of the position vector. And the acceleration is the derivative of the velocity vector. And analyzing my trajectory, the position components are here, indicates that the particle moves along the negative y-axis with respect to time. The geometry and trajectory is just a straight line along the y-axis. And then the graphical representations and make the plots for the position vector with respect to time. So it decreases when the time passes and velocity with respect to time, the velocity is constant and there's no acceleration at the plot y. And as we're talking about a line, there's no periodicity because periodicity only applies for when the motion has circular or helix trajectory. Then going to the situation number 5, we have to determine the magnetic field from a straight wire. And we know the magnetic field produced by the infinite wires given by this expression. And in this case, we must calculate the magnetic field 1 produced by this infinite wire at any point in space. So I make this tiny diagram and I use the Biot-Savart law and I replace the values when, well, first the angles in this case, alpha 2 is equal to 0 because as the wire extends, this angle is very tiny, so it gets neglectable as the wire extends to the positive infinity. And it's not the same case for alpha 1 because it's the other side of the angle, so it gets like all the half of the turn, so it gets a value of 180 grades. And then I simply replace these values at the Biot-Savart law formula, and I obtain this. Then I compute the magnetic force of the loop at each segment with respect to the infinite wire. In this case, I use this hack that the professor gave to us, and I obtained that the force of the magnetic field at the segment 1, that it's here, it's I obtained the magnetic force for each segment, and we can see the force of the segment 1 is greater than the force at the segment 3 because this distance is different, as we can see here. Well, the rho plus W, and that is the width, because the denominator gets greater or tinier. So we can make like this comparison. And the force at segment 2 and force at segment 4 cancels out because they have the same magnitude but with opposite direction. And only the segment 1 and segment 3 contributes to the net force. I summarize the net force here, and then I simply make the operations and I obtain that the formula indicates that the force of magnetic force is pointing in the direction of the positive rho. And also the two segments that contribute to the integral are attracted because they have parallel current but in the same direction that they are attracted. And also talking about the net torque, we use the formula of torque and only for segment 1 and segment 3 because they are the one that are contributing. For R, I use like a middle point because they are like the same distance, so I use the middle point to solve this. So this indicates to us that yes, we are talking about a net torque, and here are my diagrams with my forces. Then with the experimental scenario six of the velocity selector, there's well, we have a particle with an electrical force, well, with electric going in the y direction, and magnetic field going at the z direction. This particle enters the region with a velocity going in the x direction, and the particle is positively charged. Then I have to obtain the value of the magnetic field 0 for constant velocity, the initial magnetic field. I use Lorentz force, and well, first I equalize this to 0 because there's no net force. And then I make the cross product for velocity vector and magnetic field vector. And I obtain that this cross product goes in the negative y direction, and I just replace the values, and I solve for the magnetic field at initial point, and I obtain this. And now with the alternative scenario, with a magnetic field cannot be adjusted, I use the velocity vector which goes at the direction x, y, and z, and I compute this with my cross product with v0. Well, now I use this velocity vector because it doesn't tell us that the velocity only goes now at the direction of z, of x. So I make my cross product and I obtain this. And I simply replace this in the main formula, and I group the values of ay with a unit vector y with unit vector y, and the unit vector x with unit vector x. And then I separate the equation to see for which components the direction the particle experience no net magnetic force. And then I solve for my velocity vector and I obtain 0 at y, and then I solve for, in this case, the same for my velocity at x, and I obtain that the particle moves in x direction at a specific velocity, but with unique vector y. And I have here my diagram. So we can see the electrical force goes in the y direction, but the magnetic force goes in the opposite direction, even when the magnetic field goes at the positive z-axis. Well, in this case, we can see that the electric force and magnetic force cancels out as they are in opposite direction. And I summarize this in this tiny diagram. And then conceptual analysis with this step. Well, first I investigate what is a velocity vector, and I obtain that a velocity vector charged particles must move at a certain speed in order to pass through the equipment. And here is my reference. The setup works as a velocity selector because our particle has a velocity given by this expression, which experience no net force. Particle with a different velocity will experience a net force, so they will then pass through this equipment. Then talking about the relevance of this configuration, the velocity vector is used as mass spectrometer. So they used to filter particles by velocity before mass analysis. What happens is the velocity of the particle derivates from the ideal value. Well, and the particle will experience a net force and the velocity selector will lift it out. And to be more specific, if the velocity is greater than this expression, the magnetic force is greater than the electric force, so the particle goes downwards. But if the electrical force is greater than magnetic force, so the particle goes upwards at y component. Then going to the situation number 6, I use my Biot-Savart law simulator that we already did, and the subfunction for unit vector, row vector, and unit vector row remains the same. I simply modify the subfunction for magnetic field and the subfunction for, well, the main function. The subfunction for magnetic field, and I use the same at the beginning, but at the end, I convert my magnetic field intensity to magnetic field B. So I must use the permeability of free space constant that it's mu, and I just multiply my H times mu. This was the only thing that changed at my code. And then what I did was to obtain my main function, which is to obtain the magnetic force. And my function compute the magnetic force on each segment of the loop. In this case, this loop. Using the Biot-Savart simulator and the Lorentz force. In this case, I didn't use the integral because I already know the specific segment of the loop. So I asked the user to input the values of A, B, C, and D that we can see here, that are the points of the loop. And then enter the current because we can't know the magnetic field force if we didn't know the current. And then to close the loop, I add finally my 8 to close it. And I store my segments AB, BC, CD, DA, and the number of my segments in this situation of the loop. I must initialize my total magnetic force. And finally, using a for loop to repeat the code for the next segments till all of them are computed. First, this one is the beginning of the segment, and this one is the end. And I use a midpoint to obtain my observation point to compute the magnetic field. Then I did the same for initialize my magnetic field for all the segments. As we can see here, well, in this case, it's part of the function is using my sub-function of magnetic field. And, oh, got lost. Here. And in this step, my magnetic field variable is storing each magnetic field segment, each magnetic field force of each segment. And then to obtain the length of my segments, I did a subtraction of vectors, for example, of B and A. In this case, if B is here and A is here, I just make a subtraction. Then I make the cross product as the Lorentz force indicate. We can see the Lorentz force here. This cross product times the current. We already know the length to the input of the user, the B calculated at the back subfunction, and I simply print, well, add each force of the segment to the total, like the superposition principle, but now with the magnetic force. And then I print my force obtained in each segment, and finally I print the force of the loop. For reason of simplicity, I decided to print the force at each segment and not ask the user which segment he or she wants. And I obtained here. And that's all. Thank you so much. Oh yeah.